All right, let's talk about one of the biggest buzzwords out there, machine learning. You hear it everywhere, but what does it actually mean? How can a computer learn? That's what we're going to unpack today. We're breaking down the core ideas, all based on a really great introductory paper. So let's get right into it.
So let's just start with that big kind of mind-bending question, right? Can a computer really learn? I mean, when we think about learning, we think about, understanding things, grasping abstract concepts from experience. And the idea of a machine doing that, well, it's actually been kicked around since the 1950s. But the real crucial difference has always been in how they go about it.
And that's where we hit this massive fundamental shift. Think about it. On one hand, you've got traditional programming. That's where a human, a person, has to meticulously write out every single rule. If this, then that. But on the other hand, that's the machine learning approach. We don't give it rules, we just give it a ton of data and say, here you go. You figure out the patterns. You find the rules. It's a total flip in how we think about problem solving.
Okay, so here's our game plan. First, we'll nail down what ML really is. Then, we'll talk about its lifeblood, data. After that, we'll look at the two main ways machines learn, do a quick tour of the tools, and wrap up by thinking about what this all means for the future.
So let's dig in. What is machine learning? Well, you can think of it as representing one of two different cultures when it comes to data modeling. Traditional statistics, that often starts with a human making a hypothesis, right? Building a model based on some theory. But machine learning, it kind of flips the script. It often just lets the algorithm and the data lead the way. It's a subtle difference, but it's huge. It's all about being open to finding patterns you didn't even know you should be looking for.
And the jargon in this field can be a real barrier. But what's cool about this is it's kind of like a Rosetta Stone, a translator between ML and traditional stats. A lot of these high-tech sounding concepts actually have direct parallels. An ML pro says learning, a statistician says fitting. ML says features, stats says covariates. A lot of the time, it's the exact same idea, just dressed up in a different vocabulary.
All right, let's get to the bedrock, the absolute foundation of everything we're talking about. And that is the data. Simple as that. No data, no learning. So it's absolutely critical that we get on the same page about how we describe its basic building blocks.
So let's make this super concrete. Imagine a single data point is just one patient in a medical study. Okay, easy enough. Now the features, those are just all the things we measure about that patient. Their age, their blood pressure, their heart rate, you name it. The complete list of all those measurements for that one patient, that's their feature vector. And now imagine this giant multidimensional space where every single feature is its own axis. That's the feature space. That's where all our patients live, digitally speaking.
And this right here, this brings us to probably the single most important rule in all of machine learning. You've probably heard it before, garbage in, garbage out. The quality of your model is, and I mean this, 100% dependent on the quality of your data. This is where the real hard work is done. It's not just about picking a cool algorithm, it's about feature engineering to make your data more useful. It's about figuring out what to do with missing values. And, this is a big one, it's about hunting down statistical bias. Because if you train a model on biased data, guess what? You're just going to get biased predictions. It's that simple.
Okay, so now we get into the two main flavors of machine learning. First up is what we call unsupervised learning. And the best way to think about this? It's like giving the computer a test, but with no answer key. It's totally on its own.
So with unsupervised learning, we're basically handing the algorithm a big pile of data without any labels or correct answers. We just say, hey, here's a bunch of stuff, go find what's interesting, find the hidden structures. The main goal here isn't to predict something specific, it's to explore. The two biggest tasks you'll see are clustering, which is just finding natural groups, and something called dimensionality reduction, which is a fancy way of saying, let's simplify this data without losing the important stuff.
And even just within that idea of clustering, there are different ways to go about it. With a method like k-means, the human has to step in and say, okay, I think there are, say, 3 groups in this data. Go find them. But with something like a density-based method, the algorithm gets a lot more freedom. It just scours the data for areas where points are naturally clumped together, forming clusters of any shape or size, no predefined number needed.
Okay, let's flip the coin. Now we're talking about supervised learning. And honestly, this is what most people are thinking of when they say machine learning. If unsupervised learning was learning without an answer key, this time the computer gets a teacher.
So what does that mean, it gets a teacher? It means the data we give it is labeled. We show it thousands, maybe millions of examples where we already know the right answer. We show it a picture and say,
This is a cat. Another picture. This is a dog. The whole point is for the machine to absorb all these examples and learn the underlying patterns so that eventually it can make really accurate predictions on brand new data it has never, ever seen before.
But, and this is a huge but, this whole process is a really delicate balancing act. And here's danger number one, underfitting. Just look at that red line. The model is way too simple. It's like it's trying to draw a complex curve using only a ruler. This is what we call high bias. It's completely missing the real pattern in the data.
And this is the sweet spot, the Goldilocks zone. This is a good fit. The model is complex enough to actually capture the general trend of the data, but it's not getting distracted by every little random blip. It found that perfect balance.
And then we have the other extreme, overfitting. This model is just too smart for its own good. It's so complex and flexible that it has twisted and contorted itself to hit every single data point perfectly. It hasn't learned the pattern, it's just memorized the training data, noise and all. This model will look like a genius on the data it trained on, but the second you show it something new, it's going to fall flat on its face. We call this high variance.
So the big question is, how do you avoid that overfitting trap? Well, the answer is a really strict, disciplined validation process. The number one rule is you never test your model on the same data it learned from. Instead, you split your data into 3 separate piles. You train the model on the biggest pile. You validate and tweak it on a second pile. And then and only then do you get its final report card on the test set, a pile of data it has never seen before, ever.
Okay, so now that we've got the big ideas down, supervised, unsupervised, the whole overfitting thing, let's do a quick lightning round. A quick tour of a few of the most common tools you'll find in the ML Toolkit.
First up, you've got decision trees. And these are awesome because they're so intuitive. They basically work like a game of 20 questions, a big flowchart of if-then statements. They're super easy to understand, but on its own, a single tree can overfit like crazy. Their real magic happens when you bundle hundreds or thousands of them together into what's called a random forest. It's like asking a whole crowd of experts and taking the average answer. It's way more reliable.
Next up, support vector machines, or SVMs. So imagine you've got 2 groups of dots on a piece of paper, say blue dots and red dots. An SVM's job is to find the single best line to separate them. And best here means the line that creates the widest possible street or margin between the 2 groups. It's a really clever way of drawing a boundary, and it makes them super effective, especially when your data has a pretty clear separation.
And of course, we have to talk about neural networks. These are the absolute powerhouses behind what we now call deep learning. They're inspired, very loosely, by the human brain. They use these interconnected layers of neurons to uncover incredibly complex, subtle, and sometimes downright weird patterns in huge amounts of data. Patterns that human would just never, ever see. This is the engine that drives so much of modern AI, from recognizing faces in photos to translating languages in real time.
All right, so let's pull the camera back. We've talked about data, different learning styles, and a few specific tools. But what does this all add up to? What's the big picture here for the future of how we analyze things? You know, I want to leave you with this really powerful quote from the paper we've been referencing. The authors make this crystal clear. The point of machine learning isn't to completely replace human experts or those traditional theory-driven models. Not at all. The idea is that ML is a tool to enhance them. It can sift through massive complexity and distill insights that we can then use to build even better, smarter, human-driven models. It's not human versus machine, it's human plus machine. It's all about collaboration.
And that really leaves us with a final big question to chew on, right? As these machines get scarily good at finding patterns in the data, what then becomes the most important job for us, for human intelligence? In this new partnership, what's our most critical role? Something to think about. Thanks so much for tuning in.